Alright, let's go on. So, your question was, what is the relevance of internal energy in its definition? Well, we've just seen from the first law of thermodynamics, it can be expressed in this form here. And if we're talking about chemistry, we're talking about heat associated with reaction. If you burn something, it gives off heat energy. Now, in thermodynamic terms, we call that Q, but we're chemists, and chemists don't like working with Qs. They call it H, enthalpy. So that's what enthalpy is. Enthalpy is, in fact, a reformulation, if you will, of the first law of thermodynamics, if we're dealing with a chemical system. And if we now take this equation and we rearrange it, right, we get essentially delta H, which is Q, is delta U minus delta W system. Now there's a minus there because, remember, per definition, in thermodynamics, the minus means that work is being done on the system. But if work is being done by the system, we can write this as a plus. And that's how we get that equation over there. Remember, we defined P delta V as work. So if we've got constant pressure, the work done by the system, if there's expansion, is P delta V. We just derived that. So in fact, enthalpy, according to thermodynamics, is formally defined as delta U plus P delta V. Okay. And the plus sign there comes from just this idea of that the work is being done, that there's maybe work being done on the system. And that's just a formal definition. Now you can calculate this using this definition, and people have basically done this. You can calculate enthalpy changes for various substances. Now what I would like to define here, in terms of enthalpy, is the so-called standard enthalpy of formation. Standard enthalpy of formation. We'll come back to this again later. But what this is calculating the heat energy change, in other words, the enthalpy, for molecules from atoms or elements in their standard state. So the enthalpy of formation of CO gas, right, is defined as the enthalpy change of this reaction. The heat energy associated with that reaction we call at 298 Kelvin. In other words, if you do this reaction at room temperature, it's called the standard enthalpy of formation, because it's the formation of this molecule from the elements in their standard states. In other words, how they occur in nature at 298 Kelvin. Carbon, graphite, is a solid at 298 Kelvin. Oxygen is a gas at 298 Kelvin. So this, if you do this reaction and measure the enthalpy change, you record that as delta HF with the zero. We've seen the zero before in electrochemistry. It means under standard conditions. And the subscript F means of formation. HCl, the enthalpy of formation is minus 92.31 kilojoules per mole. What does that mean? It means that if you take hydrogen gas and chlorine gas, which are both gases under standard conditions, you get basically this reaction if you balance it. And if you calculate the enthalpy change of that reaction, in other words, the formation of HCl from elements in their standard state, you will get a value of minus 92.31 if you do it at 298 Kelvin. Elements in their standard state equals, so that symbol we in a calculator, again, it's very important. We have different types of enthalpy. We've just seen enthalpy of formation. You have enthalpy of vaporization. You have enthalpy of a reaction. All sorts of different enthalpy. This is another important enthalpy. this looks at the enthalpy change associated with something evaporating, right? So we don't really have a chemical transformation here. This is a physical transformation. So for example, diethyl ether, if it evaporates, it has an enthalpy of plus 29.1 kilojoules per mole associated with it. Water plus 44. So which are those endo or exothermic processes? Endothermic, because remember, if delta H for a transformation, or whether it's physical or chemical, is positive, it's endothermic, and if it's negative, it's exothermic. Now check this out. Notice the enthalpy of vaporization, in other words, the heat energy change associated with water going from the liquid phase to the gas phase, is plus 44 kilojoules per mole. It's endothermic. So if you have sweat on your forehead and it evaporates, is it going to feel cool or is it going to feel hot on the skin? Yes. Because, again, it's thermodynamics. Heat energy is going, because it's endothermic, it's putting in heat energy from the surroundings, that evaporation process. And that's why people sweat. It's nature's way of cooling you down, because the process associated with evaporation of water is endothermic. And that's nature's way of regulating temperature. Because it's pulling in heat from the surroundings, i.e. from your body, to facilitate the process of evaporation. If water evaporation were exothermic, you'd have a problem. Because then if the water evaporated from your skin, you'd get hotter. So fortunately, it turns out that the process is in fact endothermic. All right. I want to mention very briefly, I'm just going to skip this. I want to mention very briefly the notion of a phase diagram. We're moving very quickly, I know, but these are the basics. A phase diagram is the representation of any substance. Here we have a phase diagram of water, where you basically look at the phases of a substance as a function of pressure and temperature. Now we all know that at 101.325 kPa, or 1 atmosphere, water at 1 atmosphere and at a temperature of approximately 298 Kelvin room temperature, is water a liquid, a solid, or a gas? Is water at room temperature and pressure? It's a liquid. It's a liquid. Now let's see if that's right. Here's 1 atmosphere. All right. So this is the 1 atmosphere line, and here is the. This is the phase diagram of CO2, not H2O. Let me find the phase diagram of water. I was just about to say something is strange here, because I think we're more familiar with water. Just a second. It will definitely be online. So, we can discuss that. Let's see. All right, this looks like a reasonable phase diagram. All right, that's the phase diagram of water. Now, it basically breaks it down into, okay, well, we don't see the solid liquids, and that's not actually overall a very good diagram. Here we go. Ice, that's better. Now, at 1 atmosphere, so this is what a phase diagram is. It represents the states of aggregation, the states of matter, the phases of any substance as a function of temperature and pressure. That's what it is, very simply. Now, water, we know at room temperature and pressure is a liquid. And let's check this. Well, that's 1 atmosphere. This is centigrade. This is degrees centigrade. So we're somewhere around here. We're right in this region here, water. At 1 atmosphere, at 0 Celsius, we know that it's ice. So this is This is 0 degrees here. If we follow this line up and we go to 1 atmosphere, we see we're on this boundary between ice and water. 0 degrees is the temperature where water starts freezing. That's what we see in this phase diagram at 1 atmosphere. And at 100 degrees, what happens? Water starts boiling. At 1 atmosphere, we're on this boundary here where we're going from water to water vapor. Now the great thing about this diagram is it enables you to predict what the phase of matter of a substance will be if you have the phase diagram at different pressures. So let's go to 218 atmospheres, right? Look at that. Basically there, you can see that the freezing point of water decreases somewhat, because this is not a straight line. And basically, you have the notion of the two important things in a phase diagram. You have the so-called triple points. The triple points is the region in the diagram where essentially ice, water, and in this case water vapor, in other words the solid, the liquid, and the gas phase meet. It is the points in the diagram, in this case 0.01 and 0.006 atmospheres, where all three phases are in simultaneous equilibrium with each other. So the liquid is in equilibrium with the vapor is in equilibrium with the solid, and so on. It's called the triple point. Well, nothing really happens. It's just sort of the state of aggregation is difficult to imagine. At that temperature and pressure, it's essentially all three. It's a solid, a liquid, and a gas simultaneously. Sounds weird, but that's what it is per definition. We also have something called a critical point, right? A critical point, which is represented at that point in the diagram there. What a critical point is, I can actually show you pictorially what the critical point is, but let's go back to this phase diagram for carbon dioxide. See, it's very similar to water. We have, again, this is the triple point, different to water, different temperature, different pressure. Carbon dioxide is what they use to cool ice streams down, dry ice. Now, we know that dry ice at room temperature is what? Well, okay, what is carbon dioxide at room temperature? It's a gas. So here's room temperature, here's 1 atmosphere, so we're in the gas region, clearly, right? Now, if you cool dry ice down to about -80, it's solid, but it starts evaporating. So that's the freezing point of dry ice, -78. And that's at 1 atmosphere, it goes from solid directly into the gas phase. So we know that happens, it sublimes. If you have carbon dioxide, dry ice, it vaporizes, it sublimes. And we see that from the phase diagram. At 1 atmosphere, at -78, which is its freezing point, it goes from the solid to the gas phase. Believe it or not, you also have liquid carbon dioxide, which you can find in this range here. So in this temperature range and this pressure range. And the top point of this diagram, point C, is called the supercritical range. And the supercritical range is the range where the surface tension approaches 0. In other words, you can't actually see the interface anymore between the liquid and the gas. It disappears. We call that a supercritical fluid. So here we have basically for water, for water, the supercritical temperature, you can clearly see, you see a clear line between the liquid and the gas phase, in other words, liquid gas. And at supercritical temperature and pressure, that interface disappears. So it becomes like a super dense gas. It has, a supercritical fluid has essentially properties of gas and properties of liquid simultaneously. It's called supercritical. And that's always this point here on the diagram between the liquid and the gas phase. Anyway, I just want to point this out. The supercritical point, the triple point, is where you have the simultaneous equilibria of all three phases of any substance. Phase diagrams of different substances look different, obviously. And the important thing is it enables you to predict how a substance is going to behave under different pressures and temperatures. Okay. Now we get to the fun part, entropy. Who's heard of entropy? What is entropy? Disorder. Entropy is the reason why if you leave your room without cleaning it, it looks like this after some time. Entropy is the reason why things tend to become more chaotic. Why you have to clean your apartment once a week, at least, and tidy things up. It costs energy to do that. And you know, it's a terrible thing to do. I hate it. But you have to do it. And the reason why you have to do it is because there is a notion of entropy in the universe, disorder. And basically we now get to the second law of thermodynamics, which is the law of entropy, which in a very simplistic sense is that the universe tends to become more chaotic. Very philosophical. But as we sit here, according to the second law of thermodynamics, there is a tendency towards chaos in the universe. And it's an important thing to understand in thermodynamics, believe it or not. Some people call thermodynamics the arrow through time. Because if you drop a glass and it breaks, right, why can't you put it back together again? Well, you can't put it back together again because entropy is playing a role. Entropy dictates that it goes from an ordered structure to an unordered structure. You can put it back together again, but it's going to cost a lot of energy and time and effort to glue all the pieces together. And so, I mean, entropy really is the tendency towards chaos in the universe. And the arrow through time. So what we see here is a glass breaking. And that is a manifestation of entropy, the symbol of which is S. Look at that. Why does this happen? It happens because of entropy. We go from a very ordered structure before the glass breaks to complete chaos. What's driving this breaking glass is the thermodynamic principle of entropy. If it wasn't for entropy, the glass wouldn't break in this chaotic way. And you can't really put it back together again unless you spend an awful lot of time to overcome that entropy. So I think you got the point. Entropy is the tendency of the universe to become more disordered and chaotic. And it has a formal thermodynamic definition, which I will just mention. This is not really important, but this is the formal definition of entropy. S equals K ln W. Now, remember I mentioned our friend. I mentioned in a previous lecture the fate of Boltzmann, who was a professor at Vienna. Boltzmann was the guy that took classical thermodynamics, which we'll be discussing now, and attempted to make it statistical. In other words, instead of looking at things in a macro scale, he tried to break it down to see what individual molecules are doing. And he was the first person to really understand what entropy is, disorder. And he basically came up with this formula here. K is the Boltzmann constant, and W is the number of microstates. Now, to understand microstates, it's kind of like this. If you have 3 books, and you want to put them into a bookshelf, which has 3 places you can put it, how many ways can you arrange those 3 books? There's the bookshelf, right? You can put all 3 books on top. You can put all 3 books on the second shelf, and you can put all 3 on the third. That's one way of doing it, or 3 ways of doing it. But there's quite a few other ways that you can do it as well. You can put 2 books on top and 1 book at the bottom. You can put all 3, you can put 1 book on each shelf. You can put, let's say, 2 at the bottom and 1 on top, etc. The number of ways that you can arrange those books is called the microstates. And that's basically what Boltzmann said, that molecules have a certain way of arranging themselves in a so-called thermodynamic ensemble. And the number of ways that molecules, gases particularly, can arrange themselves in an ensemble reflects the entropy of the system. In other words, the more ways you can arrange those molecules, right, the higher the entropy of the system, according to this deceptively simple formula. Now that is the statistical thermodynamic definition of entropy, which we're not really going to work with. We're going to work with a classical thermodynamic definition of entropy, which is simply defined as heat over change in heat over temperature. Very simple. So the change in the entropy of a system is equal to the heat change associated with that system, which we call Q rad over temperature. All right. Now, entropy, as I just said, is associated with chaos. There's a tendency in the universe for the chaos to increase. Right? That's essentially the second law of thermodynamics in a very simplistic sense. We're going to revisit this in a moment. But if you have a positive entropy change accompanying some process, whatever that process may be, the process will tend to be spontaneous. Now you see where we're going with this. We're going towards this notion of spontaneity, but part of spontaneity is entropy. Alright, so now let's just look at this in another way. Intrinsic entropy of things. If I take a solid, a beautiful crystalline solid, where all the molecules are fixed in a nice, neat lattice, will that have a higher or a lower entropy than gas molecules flying around wildly? Which has a higher entropy? Yes. If I take an ice block versus water, which has a higher entropy? Well, they're both water, but they have different aggregation states. Ice, the solid, water, and the liquid, which has got a higher entropy. Yes. So, I mean, one has an intuitive feeling for this notion of disorder. And so you can have positive entropy changes, okay? So here we've got some examples. Let's suppose we go from solid to liquid. That's clearly is accompanied by a delta S, in other words, a change in entropy which is positive. Because the entropy of the liquid is higher than the entropy of the solid. Similarly here, we go from a liquid to a vapor or gas phase. The entropy associated with the gas phase is higher than the entropy of the liquid. So the delta S, the change in entropy, accompanying this physical transformation is, of course, positive. And so on. From an ordered system to a disordered system. Now, here's what happens. This I find very interesting and very telling sort of exposition of entropy. One can measure the standard entropy of substances using this definition here, Q over T. And if one plots the entropy, the standard molar entropy, the units of which are joules per mole per Kelvin, those are the units for entropy. If you plot the entropy of a substance, you end up with something that looks like this. Now, what's going on there? Can someone tell me? We have these discrete jumps. We start off at 0 Kelvin. 0 Kelvin is called absolute zero. Nothing can be colder than 0 Kelvin. 0 Kelvin is the temperature where things cease to move totally, including electrons. Nothing moves at all, nothing vibrates. There's no motion. 0 Kelvin, the lowest you can go. Absolute zero. Now at absolute zero, if nothing's moving anymore, what is the entropy? 0. There's no disorder. It's perfectly ordered. There's no motion. There's no chaos. If I start heating things up from 0 Kelvin, what happens to the entropy? It increases. And it increases and it increases until I reach this point here. What's happening for this substance, whatever it is? What's happening? Changes state. It goes from solid to liquid. And if it goes from solid to liquid, what do we know? The entropy increases dramatically. And so I see a discrete jump in entropy as I have this phase change. I've gone from an entropy of, let's say, approximately 80 to 120, let's say, just because of this phase change.
For elements which dissociate, like nitrogen, would that be like solid and then it goes up?
What do you mean dissociate?
Like it just goes from solid to gas.
Oh yes, yes, and not dissociate, they don't dissociate, they're sublime. Yes, then you go from solid to gas. So
it would be a much longer, like,
probably, yes, if it's sublime, that would happen, yes. Here we have a substance that goes classically solid, liquid, gas. Exactly. So now if we've undergone the phase change, what happens between this temperature here and this temperature here? Well, the heat is increasing. In other words, within that state, the liquid state, because I'm adding more temperature, i.e. more heat energy, what's going to happen? Well, the particles are going to start moving faster. And because they're moving faster, what's going to happen to the entropy? It's going to increase. Until I reach this point here, what happens here? Change of state, liquid to solid. We have a massive jump in entropy. Look at that, it's much higher because the entropy of a gas is much higher than the entropy of a liquid, which is higher than the entropy. But you see there's a substantial jump there because I'm going from liquid, which is pretty chaotic, to gas, which is even more chaotic. And then I keep heating it, and of course the entropy keeps increasing. So there is a relationship between entropy and temperature. Notice also that while I'm in the solid phase, from absolute zero until the melting point here, the entropy is also increasing, although it's in the solid state. In other words, the thing is solid and I'm heating it up. Why is the entropy increasing? Because, I mean, if it's solid, it means that all the molecules or atoms are fixed into a neat lattice. So why is the entropy increasing? Yes, exactly. The molecules or atoms which are fixed at lattice points in a crystal lattice are just going to be vibrating more, right? Because there's more thermal energy, so the entropy increases. But the entropy, you see, shoots up when you have these phase changes. Okay. Now, you can also measure the entropy, as we just saw moments ago, since we're chemists. Instead of using Q, we use H. That's a simple way of looking at it. The reality is more complicated. But let's, for the purposes of this course, just assume we can replace Q with H, enthalpy. So you can actually measure the entropy very easily by looking at enthalpic changes over temperature. And that's what people do. And that's how you get basically a graph like this. This is the formal definition that you can use instead of Q, you can use H. So that's the formal definition of entropy. Now, like I've just said, at absolute zero, the entropy is zero. Okay. Right. Now, we get to the second law of thermodynamics. The total entropy change, right, of spontaneous processes produce an increase in entropy of the universe. That's what it boils down to. If a process is spontaneous, it increases the entropy of the universe. And that's what we see here, right? We know that so the overall entropy increases according to our definition. Right. So is everyone following up until now? We have entropy, we have enthalpy. This first law of thermodynamics is the law of internal energy, expressed in terms of Q and W. The zeroth law is if A is in equilibrium with B and B is in equilibrium with C, then A is in equilibrium with C. The second law is all spontaneous processes, whether they're chemical transformations or physical transformations, lead to an increase in entropy in the universe. So that's the second law. And by the way, the third law of thermodynamics is the law of absolute zero, which I've sort of just mentioned without you knowing it. And that is that you can't go lower than 0 Kelvin, basically. The third law says 0 Kelvin, absolute zero. As you approach that temperature for a perfect crystal, the entropy approaches 0. So we've gone through all the laws of thermodynamics today. 0, 1, 2, and 3. Remember, the third law is the law of absolute zero. as you approach 0 Kelvin for a perfect crystal, in other words, the lattice is perfectly ordered, you approach an entropy of 0. And that's the third law. Second law is the law of entropy. Another way of thinking about entropy is the bedroom, the broken egg. There is a tendency in the universe for an increased entropy. In other words, the universe tends to a state of higher disorder. Chemistry, in terms of chemical terms, for a spontaneous process results in a positive entropy change in the universe. Now we've defined two terms today, and we're going to put them together in the grand equation, yes? Sorry, if the process is not spontaneous? Yes. For example, if you take iodine gas and you reverse sublimate, if you take iodine or carbon dioxide and you cool it down, what's going to happen? It's going to form solid iodine or solid carbon dioxide. Then the entropy change associated with that process is negative. It's a non-spontaneous process. So the entropy change in the universe then is not positive. The entropy of the surroundings is always going to be positive, but the entropy within a system can be negative. If the entropy change in a system is, so if you take, for example, iodine gas and you convert it to iodine solid, there's obviously the entropy change associated with that process is negative because you're going from gas to solid. So in that thermodynamic system, which is isolated, let's say, from the universe, the entropy change is negative. But in the system, in the universe, in the surroundings, the entropy change will always tend to be positive. Let's write it down in a simpler way. The change in entropy in the universe is always greater than 0 overall.
So there are no spontaneous processes which go from liquid to solid?
No.
And no from gas to solid? No.
No. Because it's accompanied with a decrease in entropy.
Yes.
So they're not spontaneous.
So that doesn't actually exist?
No.
Okay.
Now here's the thing, what this all boils down to, we can get lost in the philosophical discussions later. But what this all boils down to in a first year chemistry course is the grand equation, which we're going to end this course off with. The grand equation of chemistry. And the grand equation of chemistry is called the Gibbs-Helmholtz equation. Now, different people call this different things, depending on where you are in the world. If you're in Britain or America, they call it Gibbs free energy. Some people call it free energy. And if you're in Germany, that's called the Gibbs-Helmholtz energy, because they insist that Helmholtz, who was German, was involved in the discovery. They're all the same thing. The Gibbs-Helmholtz equation, Gibbs free energy, or just free energy, for those who want to be politically correct and leave names out of it. All of these are the same, and the equation is simply delta G, which is the symbol for Gibbs free energy, equals delta H minus T delta S. And if delta G is negative, the reaction is, or the process is spontaneous. And if delta G is positive, non-spontaneous.
So what is negative NFE?
Oh, that's just the that's also a definition of Gibbs free energy. In terms of electrochemistry, this is the thermodynamic definition of Gibbs free energy. You look unconvinced. Alright, no response. Delta G equals delta H minus T delta S. Now what does this mean? This means something very nice, because it means if you're studying a chemical reaction, now we can derive this equation, which I've left out for today. You can derive it from first principles. I'm not deriving it to you this time around, I'm just giving it to you. Basically what you can see is that by changing the temperature, you can shift any reaction from being spontaneous to non-spontaneous, or the other way around. Now what is delta H and what is delta S? These are the enthalpy changes and entropy changes of a reaction. So where do we get those from? Well, we get those from, well, this is just the formal definition, right? If delta G is negative, spontaneous, positive, non-spontaneous. If delta G is 0, it's at equilibrium. All right. All right. This is just an example of different types of basically reactions. You can clearly see that what this table reflects, with just some examples, is how we can figure out if delta G is going to be negative or positive. Of course, this is the grand equation. So if we have a situation where here's a reaction, for example, with a decomposition of N2O to N2 and O2, the delta H for that reaction is negative, i.e. it's exothermic. The delta S is positive. So if delta S is positive and delta H is negative, the result is that delta G is always going to be negative at all temperatures. Do you guys see that? Because that guy over there is negative, okay? And so it's basically just looking at the equation and figuring out how it's going to stay negative. If we have a situation like this, where we have a negative delta H and a negative delta S, in other words, a negative entropy change, it depends on the temperature whether or not the delta G value is going to be negative or not. In other words, if we can have a spontaneous reaction or not. If both are positive, then you're going to have a very high temperature to offset the positive entropy, the fact that the delta S value is positive, and so on. So basically, what this is these are the 4 different cases for spontaneity of a reaction. If the delta H of a reaction and the delta S is positive, it's the delta G is always necessarily going to be negative, because it's negative, this is positive, which means this whole term is negative, it's necessarily negative. Does everyone follow? Case 2. Delta H for a reaction. Here's an example. This is just some reverse fusion, right? Going from a liquid to a solid, freezing. Delta H is negative. Delta S is negative. Of course, because we're going from a liquid to a solid, so the entropy change is negative. If the entropy change is negative, then it means delta S is negative. So do you see that in that case, it depends on the temperature whether it's going to be spontaneous or not, because overall we want delta G to be negative for spontaneity. Case 3, they're both positive. So in other words, we have endothermic reaction, and delta S is positive. In other words, the system is becoming more chaotic, but the enthalpy change is endothermic. Now there again, it depends on the temperature. And if we have a positive enthalpy, in other words, an endothermic process, case 4, and we have a negative entropy change, for example, the conversion of oxygen to ozone, right? Believe it or not, while the entropy is going down, it's going to be non-spontaneous at all temperatures. Because no matter what you do to T, delta H is positive, delta S is negative. So this term here is always going to be positive, and a positive and a positive is a positive, irrespective of T. So we can use this equation, and it's used very often to calculate at which temperature a reaction would proceed spontaneously. And now we're going to do an example. Not the speed. Speed is kinetics. Thermodynamics is it going to happen? That's the difference.
So the value doesn't matter.
The value does matter. The value tells you whether or not a reaction is thermodynamically favorable, i.e. is it going to happen? But it doesn't tell you how fast it's going to happen. For that, you need to look at kinetics, which we did a couple of weeks ago.
So higher numbers?
So the more negative, the more spontaneous, the more thermodynamically favored. The more positive, the delta G value for a transformation, the less thermodynamically favored, i.e. it's not going to happen. But it doesn't say anything about the speed. It says it's going to happen, but it doesn't say what the activation energy barrier is. It says nothing about the activation energy barrier. That, in other words, which dictates the speed of the reaction, that is a question of kinetics. All right. Now, how do we employ this in calculations? Now, this looks scary, I know, but this is the Gibbs-Helmholtz energy, or the Gibbs free energy, or the free energy, call it what you will. And I can calculate the Gibbs free energy change for a reaction by calculating the change in enthalpy of a reaction minus C delta S. Now, how do I calculate those two values? I calculate those two values, and I mentioned this earlier in the presentation, by using something called the enthalpy of formation. So every single substance you will ever have to deal with, some poor scientist has determined the enthalpy of formation of that reaction, which I defined earlier, which is the heat energy associated with the formation of that substance from elements in their standard state. Remember, I had carbon dioxide, C plus O2 forms CO2. There's a heat energy change associated with that. And that is can be measured experimentally, is the enthalpy of formation of carbon dioxide. What is the enthalpy of formation of carbon? 0. Because it is an element in its standard state. What is the enthalpy of formation of oxygen gas? 0. Because oxygen gas has no enthalpy of formation. So enthalpy of formation is forming compounds from elements in their standard state. Those elements in their standard state, i.e. standard temperature and pressure, have an enthalpy of formation of 0. Now if I know, and the same for entropy, by the way, we don't have entropy of formation, but you can calculate the entropy change of a reaction by calculating the entropy of the products minus the entropy of the reactant. Same for the enthalpy change of a reaction. It's the sum of the molar enthalpies of formations of all the products minus the sum of the molar enthalpies of formation of all the reactants gives you the overall enthalpy change of the reaction. You can calculate it, and I'll show you how in a moment, and you can do the same for entropy. So let's have a look at that. You have tables like this. Okay, you have tables like this in textbooks, in thermodynamics textbooks, thousands of pages. And so we saw earlier that one can actually evaluate the entropy change. Remember that graph we looked at for that substance where someone heated it up and we had those discrete jumps. You can calculate entropy of a substance as well by looking at the relationship of enthalpy and temperature. Now, what we see here for a range of substances is delta H subscript F superscript O. So that's the enthalpy of formation of a range of substances. Notice the enthalpy of formation of silver is 0. Why? Because silver, as a solid, is in its standard state. The enthalpy of formation of aluminium as a solid, 0. Because aluminium at standard temperature and pressure as an element is in its standard state. The enthalpy of Br2 bromine liquid, 0. carbon, 0. So all the elements in their standard state, which means as they exist at 298 Kelvin and 101.325 kPa or 1 atmosphere, 0. But look, for example, at iron, gas, well, sorry, no, not iron. Let's take another example. Let's see if they have any other examples. No, I don't really see it. The point is just you've got to check that it's always in the standard state, and those are always going to be 0. All right, now. So you have the enthalpy change. So what that basically means, these values here that you see in this column down here, guys, is the energy, the enthalpy change associated with making these compounds from elements in the standard state, and the enthalpy associated with it. So copper sulfide, minus 53.1 kilojoules per mole, there you see it, means that if you take copper and you take sulfur in their standard state, and you heat it up and you react the two together, you're going to have an exothermic reaction, and per mole, you're going to generate minus 53.1 kilojoules. That's the so-called enthalpy of formation of copper sulfide. The enthalpy of formation of rust, minus 824, you see, highly exothermic. If you take iron and you take oxygen, to form 1 mole of this guy is going to generate minus 824 kilojoules, and so on. We, in the third column, have the standard entropy of each of these substances at 298 Kelvin. The units are joules per mole Kelvin. Now, don't get confused. Normal substances like oxygen and so on may have an enthalpy of formation of 0 because they're from their standard states, but of course oxygen gas has entropy. So look, for example, oxygen, where is oxygen as an example? Over there, you see its enthalpy of formation is 0 because it's in a standard state, but it has a standard molar entropy of 205 joules per mole Kelvin. And so that's why the symbol is S with a circle, means standard states. Now, let's suppose we have the following